today's session is a get ahead session. So what we're going to be doing is basically introducing you to these topics and hopefully just getting you feeling a lot more confident for when you're going into year 9 and when you're starting to look at these topics in your lessons. If you've seen everything once, then hopefully you'll be ready to attack the harder stuff when you go into your lessons. So my name's Halima and I'll be your teacher today. I'm a 4th year medical student. I study at the University of Liverpool. So hopefully you find this session useful. So we'll be looking at work, energy transfer and elasticity today. And these are our learning outcomes that hopefully we'll achieve by the end of this session. So we'll be looking at work and energy transfers. So we'll be looking at how a force causes an object to move through a distance when work is done on the object. So a lot of keywords. So we'll be looking at the definitions of all of these. So don't worry about that. A force does work on an object when the force displaces that object. Distance moved along the line of action of the force. Students should be able to recall and apply an equation of so what work is. So work equals force times distance. I'll just write that out for you, but we will see that. So this learning outcome is just, we'll learn how to use this equation, apply it for exams and maybe rearrange this equation. We'll look at the units. So we've got 1 joule and Newton meters. So we're going to be looking at all of our units for our energy transfers. Students should be able to convert between Newton meters and joules, and we'll be able to do that by the end of this session. Work done against the frictional forces acting on an object causes a rise in the temperature of the object. So we'll be confident with all of this by the end of that session. Part 2, so we're going to be looking at forces and elasticity. So forces involved in stretching, bending or compressing. So again, a lot of keywords, but by the end of the session, we'll be able to define them and work through exam questions in these topics. So we'll also look at why changing the shape of an object. When changing the shape of an object, we need to apply more than one force. The difference between elastic deformation and inelastic deformation caused by stretching forces. We'll look at the force in a spring and the limit of proportionally. We will look at everything. This relationship also applies to the compression of an elastic object, where E would be the compression. So I'm well aware that a lot of this kind of sounds like gibberish right now, but we will go through everything. Elastic potential energy we'll start to look at, which is one of the types of energy out of the 9 types that we'll discuss today. And we'll look at the difference between a linear and non-linear relationship between force and extension. So we'll start off with work and energy transfers. So first of all, energy and what is it? So we've got energy which can be found in a lot of different forms, and we can convert this energy from one form to another. So these are all devices or machines per se that we can use to convert energy from one force to a type of energy that we find useful. So we use solar panels and we use wind turbines to generate useful energy in a form that we can use in our homes and in industries. We've got nuclear power and then the sun, which has thermal, light and UV energy. And energy gives us the ability to do work. Without energy, we wouldn't be able to do work. Now, work in physics has a little bit of a different meaning. So if you were to say to your parents that you've done work, I don't think that it would be the same meaning as the physics definition. So in physics, when we say we've done work, what we've done is we've used energy, converted energy to create movement of an object. So that's what we call work in physics. So we're using energy to move an object. We use the symbol a capital E. So in physics, it's quite important when you're using your symbols to define something that you use either your capital if it's a capital and a lowercase if it's a lowercase. That's quite important in your exams. Your examiner might be a little bit harsh and maybe not give you a mark if you're not too clear. So do be mindful of whether something's a capital letter or not. And then the unit for energy, we measure energy in joules. And say if we were writing that we had, say, 10 joules of energy, we would use a little j like that to depict that that's how much energy we're talking about. So when we say it's joules and when we're writing it, we'd write it like this. So there are a couple of laws as well that we need to be quite confident and understand well so that we can really understand the physics behind what we're going to be talking about today. So there's a law of conservation of energy. So I think that these look quite intimidating, but actually they're not when you know what they're talking about. So the conservation of energy basically just means that in nature, energy is never created or destroyed. We're just converting it through different forms. So remember that we don't create or destroy energy. Or destroyed. So even when we spoke about, say, the solar panels that we saw earlier, they don't create energy. We're just converting that from a form that was less useful to us to a form that we find useful. So we're never creating energy, it's just being converted. Then we've got the dissipation of energy. So this word dissipation is a key word and basically just means wasted or not useful energy. So when we convert energy from one form to another, we almost always have some energy that is wasted. It turns into a form that is not beneficial for us. So say if we were operating a fan, we're converting energy from, we plug in the fan, so we're using electrical energy. It travels through, and the fan, what we want the fan to do is we want it to turn. We want it to have kinetic moving energy, and that will keep us cool. But some of that energy is wasted as sound. You hear a loud noise, or wasted as heat. You know, as you keep your fan on for a long time, the fan itself can become quite hot. So that's dissipated energy. If all of that energy that was turned into heat and sound was just turned into movement, our fan would probably move a lot faster. But obviously we can't have 100% conversion of useful energy. So we do usually get some wasted energy, and this is called dissipated energy. And then we also have our third law, which is the conservation of mechanical energy, which is basically referring to law 1 again. It's that energy is never created or destroyed. So in mechanical energy, we don't have the dissipation of energy. We have two main types of mechanical energy that I was just speaking about. So those are potential and kinetic energy. So potential energy is energy that is stored inside of an object. You can't exactly see it yet. You don't see that it's doing anything. So there are quite a few types of potential energies. So I'll give you the example that's given here is the energy that's stored in food. So it's a chemical energy. Inside here are loads of nutrients. So this is a type of chemical energy, and it's a potential energy. So you could say chemical potential energy. Another example of chemical potential energy is what we have, the energy that we have stored in batteries or in fuel. So it's energy that we can't exactly see at the moment, but it is there, and it has the potential to do work. So Other types of potential energy that we have would be gravitational potential energy. So gravitational potential energy. And then we also have nuclear potential energy. And then we have elastic potential energy. So we'll look at all of these in more detail in a bit, but basically the common thing in all of these types of energy is that we can't exactly see the energy that they have, but the energy is stored inside the objects and we can use it. And then kinetic energy is the type of energy that you're probably most familiar, and it's quite easy to understand because we can see it. So kinetic basically means movement or like a moving energy. So when we run, we convert chemical energy, which is stored inside our muscles, and we convert that into kinetic moving energy. And it's nice because we can literally see that energy. So when something moves, it's quite easy to see what the energy is converted into. It's quite easy to see that we've converted something into kinetic energy. So my Slido didn't appear to be working earlier, but we'll give it a try now. Yeah, I really don't think it's going to work today. So I might just have to ask you guys the questions. Yeah, so my Slido is not going to work today. So if you guys could put your answers to the questions in the Q&A. So the Q&A will be open. And if you would, we'll have to work through Slido through the Q&A today. So I'll put up the questions like this. And then if you guys would just, I'll give you about a minute, drop your answers in the Q&A. And then we'll read through the answers. So energy that is stored is called what type of energy? Now it's a little bit harder because you don't have the options like you usually would on Slido, but you guys have got this. So what type of energy is stored energy? Someone said there's always an issue with the Slido. Yeah, I was really excited for the Slido today as well, but just this morning it's just playing up. I'm really sorry, guys. But yeah, I've got a lot of people saying potential energy, so that is correct. Energy that's stored is potential energy. Perfect. Which has the most kinetic energy? I don't think we can do this question because we don't have the options for it. It just doesn't make sense. And this one either. So we'll look at input, process, and output. So like I said at the beginning, this topic has a lot of keywords. So my advice for you for approaching this topic is literally just to break everything down into first, what is the definition of each word? Words that we know like from everyday life they have such different meanings sometimes in physics. So say, for example, work. Learn your definitions, and if at any point you forget what a different definition was or what something is, just pop it in the Q&A, because honestly, if you don't understand one small part, it can really throw off your understanding of the whole topic. So if you want, take little notes of what we've been talking about, and maybe just the definitions, just because towards the end of this PowerPoint, we've got quite a lot of questions. And it'll be quite difficult if you're not too confident on the meanings of, say, work or power and things like this. So if you want to just jot down what the meanings are, equations and things like that. But again, I will be going through everything and I will be repeating a lot. I hope you guys don't find it annoying, but having everything repeated does help a lot. So top tip, let's go through our definitions. And I think the repetition is quite useful. So input is our initial form of energy. So what we've been speaking about indirectly is this. We've been talking about how we start off with one form of energy, we do something to it, and then we get a different form of energy. And now we've just got fancier words for it. So input is this initial form of energy. Now, usually this is the unuseful or less useful form of energy that we start off with. So let's say we'll use a runner, say. We'll use Usain Bolt, that picture that was there. So the input, what energy are we starting off with? And we said that that was a chemical energy. So we always start with one form of energy and then we do something to it. So that's our process. And that's a mechanism that transforms this energy. So in the runner, respiration occurs and we have energy being produced. So in this, and there are quite a lot of other processes that go into making muscles move, but we'll just say that the creation or the what adapts the energy forms, chemical to kinetic, we'll say respiration. And then output. So what is the final form of energy for us? So in a runner's case, it's kinetic energy that we end up with. So think about, we always start off with what energy do we put in? Input. What are we doing to it? That's our process. That's the mechanism that transforms our energy. And then our output is the final form of energy. So this was just one example, and you can apply this to any sort of machine that you see, anything in your house, really. You can look at the lamp that might be next to you and then apply this. And I think if you do that, like as you go around, it will help to kind of solidify this process in your mind. You can keep trying to work out what type of energy is going in, what's happening to it, and then what form of energy is our useful energy, and then even think about what forms of energy are being dissipated or are wasted. So again, Slido is playing up. So let's see. So the Slido question that we had was, calculate the potential energy of a cat, of a 2 kg cat perched 10 meters above the ground. So I don't think we've actually shown the equation for potential energy yet. That is times. Okay, I think our sliders are messed up too. So it's not going too well today, but we will have a very good session. Let's start off with this question then. So in science, work is defined as, and it's a lot harder because you don't have the options, but can you guys in the Q&A pop your definition for work? What is work? What would you say the scientific definition of work is? That's great. So a lot of you are putting your answers in the Q&A. So that's great. It's transfer of energy from one form. A lot of you saying. Perfect. Energy used to transfer. Great. So all of your answers are along the same lines, which is great. So in physics, we say that the definition of work is when we have energy transferred from one object to another. So it could be a human to an object or one object to another, and we use a force to displace that object. So simplest way to kind of break it down would be if I had my pen just laying on the table. This was literally just laying here, and I just push it. So what we've done is we converted one form of energy into another, and we've done work. So it's the movement of an object by applying a force. So my finger is the pushing force, and somebody actually put the equation into the Q&A, which is great. Work equals force times distance. So the force applied times by the distance that the object traveled. So we'll look at this more now. Don't worry about that. But yeah, great definitions, you guys. So mechanical energy is equal to the sum of kinetic energy and something else energy. So what is this other type of energy that makes up mechanical energy? If you remember earlier, we spoke about two forms. What was that other form? So a lot of people, the correct answer is potential energy. So remember that potential energy is the correct answer. But remember, when I gave you the list of other types of energy, what I meant is so when I said chemical and gravitational potential energy, when we spoke about nuclear potential energy, these are all types of potential energy. So it's kind of like this is your heading, and then these are all subtypes of that type of energy. So try not to get confused between the subtypes and the main groups. I know that there's so many words and kind of groups and everything going on, but today what I want is just for you guys to feel comfortable with what is mechanical energy. We've got mechanical, we break it down into kinetic and potential, and then we can break that down even further. So our potential energy has lots of different types, can't speak, but lots of different forms of energy underneath that. Okay, so great job. So we're going to keep talking about this input, process, and output. So these are just a couple of examples that I've got lined up for you throughout the next few slides. So if we look at, in this case, a car engine, what we've got is energy being input as usual, and in this case it's chemical energy. Now, like we said, fuel has chemical energy stored within it. Another example of chemical energy would be the energy that's stored in food, batteries, and inside our muscles. So we've got chemical energy coming from our fuel. We put it inside the engine, and the engine is a machine that basically is converting our energy forms. So we get our useful energy output as kinetic energy, and then this is transferred to the wheels of the car, which will make your car move. So this is the useful energy, the form that we want. But like I said, if you can keep trying to kind of visualize the process and think about what other type of energy forms are we creating that are less useful? So just give it a little think. So whenever you see a process going on, think about which ways is energy dissipated, in which ways is it wasted. So I'd be thinking in an engine, you have a lot of heat generated, which isn't really useful. You don't need your car to heat up. So a lot of heat and sound. So those two forms of energy are wasted. So we have heat and sound and probably others, but these are our dissipated energy forms. Okay, and then we've got another example here. So let's take a light bulb as our next example. So what energy do we put into our light? Electrical energy. We turn on the light switch and electricity flows through the wires, through our lamp, and then creates an output. So our process is being carried out by the light bulb. So that's the conversion of our energy, and the useful form of energy again is light energy. But like I said, think about what type of energy forms are being wasted, because these are quite common exam questions. So if you can try to predict all of the questions that your examiner will ask, you're less likely to feel overwhelmed or shocked in your exam situation. So I always recommend try to kind of predict what kind of questions could your examiner ask. So this is such an easy question. He might give you this example and then say, what are your dissipated energy forms? Give an example of a dissipated energy form. So with a light bulb, if you've ever touched a light bulb, which I don't recommend after it's been on for a while, it gets quite hot. So we've got heat energy, and that heat energy doesn't help to light up our house. So we don't really want that. Sometimes you can hear sound, and so heat energy is thermal energy, to be more scientific. I'll correct myself because, like I said, physics is so much about keywords, so this is way better to say thermal energy. So I'll correct myself. Thermal energy is our dissipated energy, and light energy is our useful energy output. And then we've got other examples. So if you guys want to take a second and think about what's our input and what's our output. And then if you want to think about any dissipated energy forms. So what energy do we put in? What do we get out? So I'll give you guys a few seconds before I go through it, just to have a think of both of these yourself. Okay, so hopefully you've had a second to just think about the energy forms that are going in and out of these. So we spoke about this before, but with a fan, we've got a wire attached to it usually, or some sort of batteries, which would be, if it's a wire, we'll have electrical energy as our input. And then the motor inside the fan will do the outward process. So it will convert our electrical energy into kinetic energy. So our fan starts to rotate, and that's exactly what we need to create a nice breeze on a hot day. So yeah, so the motor inside here is doing our process. Sorry about my handwriting, it's atrocious. And then here we've got a little bit of a different input. So we don't exactly plug our wind turbines in. Wind is a type of mechanical energy. So if you think about it, wind is moving. So it's a type of moving energy. So it's kinetic energy. If anything moves, it's kinetic energy. So we put it in, we get rotation of our blades, and then our output would be different in different cases. So it depends on what that energy is converted into. So in some cases, that is converted into chemical energy or electrical energy. So say if we wanted to produce electricity from this, but in your exam, not to worry, they would usually tell you what's happening with that energy so that you can work out which form of energy it's being converted into. And we're going to have a look at different forms of energy now. So in this case, we've got a human pole vaulting. So I think it looks a little bit intimidating when you're trying to think of the energy forms that we've got going on, but actually it's not too bad. So think about what happens during a pole vault. We have a man who runs first. So the first energy that's being put into this situation is kinetic energy. This man physically runs, and then we have energy transfer into this pole. So the pole starts off at a shape like this and then becomes this. So it's bending. So this type of energy transfer is elastic. So some objects have elastic potential energy. So this stick in this form has elastic potential energy. It has the potential to bend and then return to its original shape. So we've got kinetic energy from the human being converted into elastic energy in the pole vault. And then again, a similar process is happening here in archery. So what we've got is a person who's again applying kinetic energy. So the woman will pull back on these strings. So she's applying kinetic energy, which is being converted into elastic potential energy. So when she deforms these strings would kind of stretch outside of their normal shape. So we've got elastic energy. And then finally we get this elastic potential energy when the woman lets go. These strings would return to their normal structure or shape, and then we'd have kinetic energy again. So there'd be another conversion of that energy. So then we have elastic going into kinetic again. So this process, you can see all of the energy transfers that are going on. We've also got, say, a speaker. So if it was plugged in, it would be an electrical energy input. If it was operating by batteries, if it was much smaller, what type of energy would that be? That would be a chemical energy. So chemical energy, remember, is stored inside things like food, batteries, fuel. So if anything's battery operated, chemical. If it's through a wire, it's usually going to be electrical energy. And then the speaker does our process for us and converts our energy into sound, which is our output. And then again, solar panels. So what is our input? So it's solar energy, but that's not actually one of our 9 forms of energy. So the 9 forms of energy that we have, if I list them off for you, so we've got thermal energy, light energy, electrical energy, kinetic, sound, chemical potential energy, nuclear potential energy, elastic potential energy, and gravitational potential energy. So solar power, or solar energy is not exactly one of these forms, but solar energy or light from the sun has a mix of thermal energy. We know that the sun's rays are warm. They also have light, and they also have UV radiation. So in this case, what we're doing is we're converting one of these forms of energy, so it's usually light energy, that we convert is our input, that we convert into electrical energy to power homes, or on a larger scale, we could power businesses and things like that. So we've got another example would be a falling ball. So in that case, we're thinking about another type of energy. So if we were to hold a ball and literally just let it go, what energy is being converted in that case? So the ball, once it's above the level of the ground, has gravitational potential energy. And that basically means it has the potential to be pulled downwards towards the center of the Earth by gravity. So we call that in physics the direction that gravity pulls something, it's always downwards. So we know it doesn't matter where in the world you are, but we just know that gravity is a downwards force. Okay, so if we were to literally just let a ball go, that is gravitational potential energy becoming kinetic energy. Okay, so just the ball being up there, it had gravitational potential energy, and as it falls, that's moving, so kinetic energy. So we spoke about work earlier, and I got you guys to tell me the definitions, which you guys did amazingly. So work is a transfer of energy from one form to another, and most of you said that in your definitions, which was amazing. So there's always a force that does work. So we've got our equation to work out what work is. So work is a change in energy. So this little triangle is a delta, but it basically just means change in energy. So whenever you see this, you might see it in chemistry, you might see it in biology, but it basically just means change. So change in energy is what that means. And then somebody actually wrote this equation out, which is amazing. So work equals the force that we apply times by the distance that that object travels. So we've got a little example. So if you guys want to have a go at working through this with me, that would be great. There are loads more examples to go. So you guys will have a chance to go through some questions and have a go. So we'll start off with writing out our equation. So work equals force times our distance. So a stick man pushes a box with a force of 20 newtons for a distance of 3 meters. How much work did he do? Just before we go through the question, I just want to note that for this equation to work, we need to have our units correct. So force is always measured in newtons, and our distance is always measured in meters. Okay, so if our question was to give us, this question's perfect, it's given us the units that we need, but if it didn't, and in part B you can see that it hasn't exactly done that, what we need to do is convert our units first. Convert our units and then work out using our equation. So we'll start with part A. So we want to work out how much work has been done. So we know that work done equals force times the distance traveled. So it's equal to the force that was applied in newtons, so 20 newtons, times by the distance in meters, and by 3. And we get the work done is, I had to double check that my math was right. Oh my God, I haven't done math in so long. But yeah, so the work done is 60, and I believe the unit is joules. Joules. Okay, so that's our answer. And then for part B, like I said, the examiner has tried to trick us a little bit by changing the units. So this is something that you'll see in your exam questions as you go along a lot. So sometimes, especially in an exam situation when you're feeling quite stressed, you're focused on so many other things, it's quite easy actually to forget your units. So that's one thing that actually I usually do at the end of an exam paper, just go back and make sure that I haven't been too stressed and missed out something like this. So I make sure that my units are correct, and I'd recommend that you guys do the same. So just looking at things like your conversion rate. So we've got a stick man pushes a box with a force of 3 kilonewtons for a distance of 4 centimeters. How much work did he do? So it's the exact same equation, and it'd be very easy to just plug in 3 times 4 and work out our answer. But actually, we've got a little bit more work to do because we've got to convert our units. So 1 kiloneutron is equal to 1,000 neutrons. So if we want to convert kiloneutrons to neutrons, which is what we want to do, we need to times by 1,000. And I always do this in my exam, even if it's a simple thing like centimeters to meters. I usually write this out because, like I said, in an exam situation when you're stressed, it's very easy to make very silly little mistakes. Like if you were to get your conversion rate wrong, you're losing marks for literally no reason. So writing things out, your examiner is never going to look at that and think, oh, what was that kid doing? They will not care. Honestly, just go for it. Do whatever you need to do to secure your marks. So for me, that's write out my conversions. So 1 kiloneutron is equal to 1,000 neutrons, and we've got 3 kiloneutrons. So that's equal to 3,000 neutrons. Okay, and then we've also got to convert our 4 centimeters into meters. So like I said, a lot of you will just do this off your head, off the top of your head. Sometimes I might write down my conversion rate just to make sure that I'm doing it correctly. So 1 meter is 100 centimeters. So if I want to get from 4 centimeters to meters, I need to divide by 100. So 4 divided by 100, I usually do my math like this. So we've got 0.04 meters. And now we're ready to work out our calculation. So the work done is equal to the force, which we worked out was 3,000 and by 0.04 meters. And I'll just grab my calculator. So the answer is 120 joules. Okay, so I'd say as another tip of mine would be whenever you've got calculations, especially in exams, no matter how simple it may seem, I would always double check with a calculator. I wouldn't do this in my head thinking that I can, even if I was super smart, just because sometimes we can make silly mistakes under stress and we don't need to lose marks just because we got something wrong. And this is something that I try to tell my brothers and they don't listen to me and they end up losing lots of silly little marks. And so I 100% recommend just double checking your answer with a calculator. You know, it only takes a fraction of a second if you've already got your calculator next to you. So 100% I recommend just double checking your answers. There's no harm in being overly cautious. So does anybody have any questions about that calculation? If you do, just let me know in the chat before we move on.